Hello. Today it's the sixth video in the series, and I'm going to be going over manipulating registers. And this is a prequel episode to, well, the next episode, which is going to be on using a 7-segment display. And this video today goes over a concept that's going to be important in that next video. So without further ado, let's take a look. What I have in front of me is the exact same program we ran in the last video. It's just the blinking LED program. I've added a few lines to it. This line should look familiar. That's the one that inverted the pin each time this pause finished. And then I added those two lines and this line. Before we take a look at this, I just want to say I also added up here notes on setting the tri-state registers, and in that I just went through saying that each bit within the register corresponds to an I/O pin on the device. And if you look in the data sheet at the TRIS-A register, it's a 32-bit register, so it's made up of a 32-bit binary number, and this line is what the register might look like if you set some of the pins. In this example, I only set the integer 1 or index 1 pin, which corresponds to RA1, which is what we set before down here, which is why I have a TRIS-A equals 0, because that's setting it to be an output. If you remember, 0 is an output, 1 is an input. So I just kind of drew up this little table saying here's bit 31 if you read vertically, and bit 0. Bit 0 corresponds to this bit, which corresponds to RA0, and so on. And for the PIC32MX250F128B, if you take a look at the data sheet, there are only RA0, RA1, RA2, RA3, and RA4 pins. So I only included those because they're the only ones that I consider relevant. And then here's just that note again on that 0 is an output and 1 is an input. So this might be something you want to, if you didn't understand why we set the tri-state register, maybe take a look at that, read through it. Hopefully it made sense. But let's get back to this. If you have experience with PIC32s, you're going to want to skip this video. I'm just going over binary, hexadecimal, decimal, and constant representation of registers. So if you know how to convert from binary to hex and you feel comfortable setting registers using binary and hex, just skip this video. It's not for you. This is just for myself later if I want to reflect on this stuff, or if I'm trying to come up to speed again on this later in life, or for people who don't have any experience with that, with these concepts. So again, I added this line and these two lines of code. I'm going to go ahead and run this on the device, and I'll just let it do its thing. But let's see what it does. It's going to take a second to program. Okay, so it's running. And if you remember last time, this program just made the LED blink off and on at a pretty quick rate. And it did that by using this line of code, but now nothing's happening. If you take a look at the board, our LED is not blinking. And what's up with that? Well, what do these other three lines do? Well, let's take a look at that line that we already had. It was lat-A invert, so we told it to invert the RA1 pin. And somehow that was we told it to do that by lat-A invert equals 0x0002. And I guess if you've never programmed PICs before, this whole line might seem like an enigma, or just something you might not know what's going on there. Well, actually, all four of these lines do the exact same thing. And what happens if you invert something twice? It's basically like you didn't invert it, right? So what happens if you invert something 4 times? same thing. It started off, I inverted it 4 times, and so it stayed off. So actually the program's running perfectly, but it's not blinking because I've inverted that pin 4 times each cycle, so it's essentially doing nothing visually. Okay, so let's break down what this line does. But actually, since I already said that each of these lines do the exact same thing, let's break down this first line. What is this line doing? So this lat A invert basically tells the chip to go in and go to the lat A register and invert every pin that I'm telling you to. So 0B, if you have a number that starts with 0B, that means it's going to be a binary number. And since lat A is a 32-bit register, I have 32 zeros and ones over here. And if you have trouble counting that, hopefully you can just take my word for it. But they are there. So I told it to invert, but it's only going to invert pins that are set in this number. So which pins are those? Well, it's not inverting the 0th or any of the other pins except for the 1 pin. And if you remember, our RA1 pin is on not the 0th, but the 1th pin of the lat A registers, the port A register, and the tris A register. So what this line does is it comes in and it says, hey, I want you to invert lat A on none of the pins except for the RA1 pin. Oh, nice. This next line, which was the original line we had in the previous video, does the exact same thing, except this time it's in hexadecimal. And I'm going to talk about that in a second. Maybe if you're familiar with them, well, like I said, if you're familiar with them, you really shouldn't watch this video, otherwise you're just going to think, well, you're going to hate me because it's boring. But and then here, this line does the exact same thing, but this time we're using a decimal number. So decimal numbers are your standard digits everybody learns in school, 0, 1, 2, 3, 4, 5, up to infinity. Just integers. And then this very last line is come into lat A and invert the port A RA1 mask. And that might seem a little confusing, but if you had to ask yourself what would this line be, well, it's some sort of name that says I only want you to invert the RA1 pin. Okay, so let's take a look at, well, let's take a maybe more of a just a little bit more of a look at each of these. So I wrote those commands out, well, starting with the binary again. This is that first line that we took a look at already. And I showed here that you can represent it in 3 different ways. Each of these lines is identical. So anytime you type in a binary or a hex number, you do not have to give it all 32 bits. If you give it only 4 bits, it's going to say, okay, I know that the bottom 4 bits are these, and it assumes everything above that is a 0. And same for only 2 bits. You could even give it 1 bit. 0B, 0 would be 0. Man, that was a mouthful. But that's how binary looks. You can type in a binary number by typing 0B and then however many bits you want in a way that makes sense to you. So again, since our RA1 pin is the 1th pin or 1th bit in the register, that's the one that gets set. Okay, if you're not familiar with hexadecimal numbers, I'm going to break those down a little further in a minute. But basically, if you want to convert from binary to hex, a hex digit is made out of 4 binary digits. So in this example, 4 zeros is a 0 because 0 is 0. But a 2 is represented by the number 2. So that's why up here, this hex value, and you can tell that you're using a hex value by this 0x indicator. So 0x, this is going to be a hex number, and it's 0002. Okay, what number would that be in binary? Well, if you can mentally exclude the upper half of these, or even if you want to take a look at this guy, from binary I have 0, 0, 0, 0, 0, 0 all the way down to that 1th bit, but here all those zeros make up a 0, all these zeros make up a 0, because again, converting from binary to hex, it's 4 bits make up 1 bit in hexadecimal, another 0, but then over here I have a 2, so 0x0002 is equal to 0x0002. Since this is binary 2, it's represented by the decimal 2 in hex. And that gets a little more complicated, and I'm going to go into that in a second. But hopefully that got your curiosity going. And so, same as with binary, in this top case, this is giving it all 32 bits in the register. And how do we know that? Because I have 8 digits here, and each digit in hexadecimal represents how many bits in binary? 4. So 8 times 4 is 32. That's how you get that. But again, you don't have to give it all 32 bits. Here you can, and in the original program we only gave it 16. So it assumed everything above those 4 was a 0. Okay, here is the decimal value. So hopefully if you know what binary is, you can convert from binary to decimal pretty easily. 0010 is a 2, which is what this guy was, and if you had a 1000, it would be an 8, and so on. Okay, and then this last bit is the fun part. So I'm going to go ahead and, well, I'm going to see if you can do it while it's commented. This lat A invert equals port A R1 mask. What the heck is that thing? If you're not familiar with C programming, you can define constants. And if you ever come across something, well, here, I'll uncomment this. And hopefully, see how it turned a different color? That means that it's defined somewhere. And so anytime I have something like that, if I leave the cursor on it, and I do a right click, and this menu pops up, if you go to navigate, go to declaration or definition, it'll bring up whatever header file that's stored in, and highlight it automatically for you in that file, which is really handy. And so if you're ever browsing code online and you see constants defined, that's one way to look up what they are. So if you take a look at this line, it says, I'm going to define a constant, this is the name of the constant, and here's the value. And if you notice, we have this 0x signifying we're using a hexadecimal number again, and it's going to be 7 zeros, so 1, 2, 3, 4, 5, 6, 7, and that 2. And if you remember, that's what we said it would be right here. So I can give it this name, and it will understand that what I mean is this number. And again, this name, as you learn more about programming, a mask is usually something like this, where it's a way to use a name that is human readable to represent a number that does something physically on the device. So here I told it to invert port A R1 mask, which means invert the RA1 pin the same way as all of these do. Okay, and so if you notice, I've got all 4 of these up there still, and now I've got a 5th one. So if I run this, it is going to blink for us. But in the meantime, you might be wondering, okay, why would I want to use each of those different things? And why did they give us the option to use all those different things? Okay, so now we've got our LED blinking. Hopefully that's not bothering anybody. Sorry, where was I? Oh yeah, why would we want to use each of these different representations? What's their benefit? Honestly, depending on what you do, it's going to make things more readable. So again, if you use this constant, I mean, that's pretty easy to read once you know the name of the pin, so RA1, and you know that it's a mask, so that means it's a number representation. And so I'm here, this is pretty easy line to read. It says, I want you to invert lat A, and I only want you to invert that pin. Pretty handy. Binary, the one nice thing about binary is this is literally what the register is going to look like. It's not made up of decimal numbers or hexadecimal numbers. This is kind of a nitty-gritty way of looking at the register and saying it's made up of ones and zeros, and I know that the RA1 pin is the 1th digit in that register, and I want to set that one. So if you really liked to visually understand what your registers are doing, binary is one way you could go. But if you look at the disadvantage of it, I mean, look how horrible it is to read a 32-bit number. And let's say I had a couple more digits up here, so let's say I set something like this, and then I didn't care, I didn't define anything above that. Well, now if I want to know what pin this is, I have to come over here and count over. That was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then I gotta know what pin that is. And it's just a lot of work. And again, if you type this out, you'll probably know what pin it is, or you can leave a comment to help people out. But if somebody comes in and they're trying to read your code, it's gonna take them time to understand what that line does and what pins it's setting, and so it might not be the best way to go. But maybe if you're playing around with things and you want to know exactly what bits you're setting, that might be a good way to go. Hexadecimal. When I was learning in school, my professor loved hexadecimal, and honestly I think it's very useful to use too. It's powerful in that I can represent a big register with only a few digits. So here I'm only using 16 bits, but I'm representing 16 bits with 4 numbers, which is very easily readable. I don't have to guess it, like visually I can see, oh, that's the 0th and the 1, and it's not hard for me to understand what pins are getting set in the register, or what group of 4 pins are getting set in the register more specifically. And again, I'm going to break down hex in just a second, so hopefully it'll become more apparent why that might be a popular choice. And decimal works mathematically, but it's very, very confusing. For example, let's say you wanted to set these pins the same way we did up here, and imagine turning this into a decimal number. I guess I should have picked a number that I would know, but let's say it's probably not, but let's say this number was something like, oh god, I don't know, 40,835. I know that's not right, but just imagine looking at this number and trying to identify what pins are getting set, or what pins are getting inverted in this case. It's really hard to convert from decimal to binary in your mind. Actually, it's a lot easier to go from binary to decimal, at least for me. But to take this number and know what pins are getting set is very difficult to do. So a lot of the time binary is never used for operations like this, but it is possible, just so you know. So I'm going to erase this since that's not going to run. And you know what, I'll just comment this line out. Whatever. Okay. So now I'm going to talk about hexadecimal a little bit more, just for the people who've never used it, just so they can see it. And the reason that hexadecimal is going to become so important is going to become apparent in the next video, where it simplifies everything. So let's take a look at this. This is a different file, but you know what, I'm going to take this. I'm going to put it in the other file too. That way when I put this on the website, it'll be there for you guys. Okay, it's indented a little weird, but that'll be alright. Okay. So again, each digit of a hexadecimal number is 4 binary bits. So you can break it down in something like this, where you have 0x807F corresponds to a hexadecimal number that's has 4 digits, and each of those 4 digits is going to comprise 4 binary bits. So what do we know about a group of 4 bits? How many values can that represent in a decimal number? Well, 11111 is 15. So if I wanted to give each of these digits, each hexadecimal digit, a number to represent it, let's say I do 1001. Well, that's 9 in decimal, so 9 will be represented in hexadecimal by that same number 9. But after 9, you get into double digit in decimal, so 10, 11, 12, 13, 14, 15. And to get around that with still using only one hexadecimal digit to represent those numbers, after 9 it goes to alphanumerics. So it's in hex you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And after F it stops. This would go to 0 and you'd have a 1 in the next column. Similar to binary. But here I gave you a table of how the numbers break down. So a 0 in decimal looks like a 0, obviously. It's a 0 in binary, and then it's a 0 in hex. The difference being 0B and 0X for the identifiers for each of those. And then as you go down the line, 10, I love 10 in binary, it's just 10, 10. And this is kind of a neat row for me, where 10 is 10, 10, and then it's also A, which is where it changes. So it's just kind of an important row in my mind. But keep those in mind. Here's a couple examples of hexadecimal or binary to hexadecimal. So let's start with this number. And what you do is you want to section off each four digits of your binary number. So I put a space in between each of those. Just makes it easier visually. And I know that 1111 is 15, and so if I go back up to that table, I know that 15 is 1111, and that corresponds to F in hexadecimal. So those 4 bits are an F. 0111 is a 7. So I come up here, 70111, and 7 in hexadecimal. 00, nice and easy across the board. And then 1000 is 8. So 8 is 8. So this 0B, 1000, 0000, 01111, and then 11111 is equal to hexadecimal 0x807F. So nice and easy. Let's take a look at this next one. We've got 0B 1010. Well, I know that's a 10, and that's my favorite row, so 10 is an A, because that's where it changes. This next guy is 1001. That's a 9, so since it's below 10, it's just whatever number it is in decimal. Here I've got 1110. Honestly, off the top of my head, I don't know that one. But if I come up here and look at my table, oh, there it is, it's E. So, E. And here I have 0001. Well, that's just 1. So this number would be 0x A9 E1 in hexadecimal. Okay. That's getting towards the end of the video. The only thing, I'm just going to tease why this might be important. In the next video, I'm going to be showing you how to represent numbers on a 7-segment display. We're going to write, I think it would qualify as a definition of a driver. We're going to be writing a driver for a 7-segment display. And to do that, we're going to be turning on whatever number of LEDs we need to represent each number. So I'm going to be turning on several pins in a register, and if I wanted to represent that with a constant, like we had that nice constant back here, well, I can define my own constants, which is something we'll take a look at, but they're not available to me right away. I could use binary to represent each bit that we're going to be setting, but And that actually is a good solution, but it just makes it nice and easy to read. It's nice and compact if we use hexadecimal. And just as like a teaser, this is kind of the code we're going to be writing. So we're going to be defining a function, which is something we haven't done yet, and then depending on what number we want to represent on our 7-segment display, it's going to output each of these. We're going to set latches to be what we want them to be. So if we want it to be on, it's going to be set to a 1, and each of these pins is going to break that down. Hopefully that wasn't too abstract today. Hopefully I've helped. If this is something you've had questions on, this video helped you a little bit. And that's just another look at setting registers, and so hopefully that made sense. Thanks.